Okay, kids, back again to 4.4 Part 2, Modeling and Optimization. The topic is, or the idea here is fabricating a box or making a box out of a flat piece of cardboard. So an open top box is to be made by cutting congruent squares of side length X from the corners of a 20 by 25 inch sheet of tin and bending up the sides. Write a volume V of the box as a function of X using appropriate units. What is the relevant domain of V of X? So the way I look at this, I kind of picture it folding up, and you can see that I have highlighted the length and then the height and the width as it would fold up. So it's kind of coming out at you. And then notice that if I have a full length of 25, that length in pink is going to be 25 minus 2x. So that's the pink length that you see at the base of the box. Okay, so 25 minus 2x. And then the width, so I have the width then, so over here, so we have 25 minus 2x. So you see you have 20, and those are in inches, 20 minus 2x here. And then we, of course, have the height of the box is x as we fold up those sides. So 20 minus 2x, and then we have x for the height. So we know that volume is equal to length times width times height. Oops, didn't mean to cover that up. Is equal to length times width times height. And so when we get our answer, we're just going to take, when we get our expression here for volume in terms of one variable x, we're just going to take the length, 25 minus 2x, and we're going to multiply it by the width, which is 20 minus 2x, and then we're going to multiply it by x. Now, the smallest x is going to be 0. So when we're asked, there's our volume expression, but we're also asked for the relevant domain of v of x. So what would be the endpoints of the interval? You kind of get that feeling of the extreme values of whatever x could be are going to affect the function itself in the extreme values. So we're going to say, all right, we know we can use 0, but the problem with 0 is that you have no box, right? So you could still be talking about the box and saying, guess what, kids, you have no box. But then if I look at the units here, x, or the dimensions, the dimensions 20 minus 2x, think about when that's equal to 0, x would be 10. Now when the first one would be equal to 0, it would be 12.5. So the 10 would be more limiting. So the domain would only be, the domain for x there is only going to be from 0 to 10. So that's the rest of the story for the first part of that problem. I think I need to turn off my fill on my squares and so. Okay, so there we go. So we answer the first question. We have the dimensions, and then we have the volume, okay? So now if we go up, I wrote the volume a little bit differently. So for part B, we're being asked to find dV/dx using appropriate units. I think there was a T there, so I had to make a correction. So finding dV/dx using appropriate units, interpret the meaning of dV/dx in the context of the box. So when we do, like I said before, the dV and the dx make it kind of easy to see what the units should be. So we know that the top is going to be inches cubed and the bottom is going to be in inches. So you're comparing inches cubed volume with inches, the linear measurement. Okay, so finding dV/dx. Finding dV/dx, we simply have, as I multiply it out like this, it's easier to use the power rule. Remember, I do have the product rule for this type of equation with 3 factors, but we'll go ahead and multiply it and then take the derivative for that. So part B. So we get v prime of x is equal to 12x squared minus 180x plus 500. Okay. When squares have side x, the ratio of the change in volume of the box to the change in the length of the side of the squares is then 12x squared minus 180x plus 500. Now, in this case, I have this kind of early. I want to get the critical number here. So this kind of goes with that. We've answered this, and this is in inches cubed per inch. Okay. when we see that, we're just comparing the volume with the inches on the side, the volume with the side, the height of the box, actually. Okay, so what we're going to do is find the value of x that will maximize the volume. So I'm going to use this space since I have a little extra there, and I'm going to say 12x squared minus 180x. So this is really the answer for part B, but just using the space here. So that is equal to 0. So if I want to solve that equal to 0, solving, it is a quadratic, easy to solve. You either use the quadratic formula, factoring, sum method. In this case, you could use a calculator if you wanted to. But in this case, I'm just going to say with the quadratic formula, I get x is equal to. So the critical numbers, I'm going to put that up here, of the derivative are x is equal to 3.681, and I think it's past the domain, it's 11.319. So those are the x values that will cause the derivative to be equal to 0. Now the problem, let me get the style turned off here. No fill on that. So the problem with 11.319 is that that is not on the allowable domain of the function. We're only dealing with just from 0 to 10. So we're going to ignore that critical number. Even though it's a critical number of the function, it's not in the domain of the volume we're dealing with. So now remember what we do. We want to find the value of x that will maximize the volume, right, in part C. So setting the derivative equal to 0 and solving, we find the roots. And because the larger root is outside, we ignore that. Now we're going to apply the candidates test. Remember with the candidates test, we're going to compare v of the endpoints. I'm going to put EP here for endpoints with compare. So you're going to compare those with v of the critical number. In this case, there's only one. So there's two endpoints. So if you notice, if I have v of 0, I hope this is kind of easy to see. If you put 0 in for here, can you all agree with me that you're going to get a 0 for the volume? In fact, if you use 10, that second factor that I'm pointing to here, up in part B, that's going to be equal to 0. So you're going to end up with a 0 volume there as well. So when we put in 3.681, it looks like we get a volume of 800, I'm going to put blue ribbon there for that, 820, let me erase that, 820.528, and that would be in inches cubed then. So the maximum volume, so this would be the maximum volume, and you can get your graphing calculator out, and if you look at the function that I put in for the volume, you can see it's not in factored form here. So I have the volume up there, and then you can do that. Remember, it's second trace, and you're finding the maximum on, so you want to second trace and then find the max. You're going to have to get a left bound, right bound, and so forth to answer that question then. But second trace max in the calculator. So you can, what's really nice about this, say even that you can't use this on some questions on the AP exam, you can certainly use your graphing calculator as you're trying to make sense. Sense making is really important of what this is, because it might be a really abstract graph. What does it even look like? It's actually part of a cubic graph, okay? And if you look at it, you're at 3.68, so you're somewhere over here with 11, you're at 0, 1, 2, 3, 4, 5, 6, 7. I can't remember what the scale was, but if you count the units, I think they're each one. So on that window, you're not using the whole graph for the volume. You're only using from 0 to 10. Okay, so we have a maximum. So when the squares, now we know what x is. When using appropriate units, interpret your answer in the context of the box. Remember, you're going to go back to answer the question here. So we have the volume of the box expression, and it just says interpret your answer in the context of the box. That is for this question. So when the four squares have sides of 3.681 inches, the box will hold a maximum volume of 820.528 inches cubed. So again, use technology where it's meaningful to support your learning, and go through the process of examining all the steps that we talk about with the 4.4 optimization problems. Now, the next one I'm going to look at is designing a can. So you have been asked to design an oil can, here let me cross off the D, an oil can shaped like a right circular cylinder. What dimensions will use the least amount of material? So when you're making a can, the material is the surface area of the can, right? So that's what we want to optimize. And in fact, this is going to be a minimum, right? We want that to be a minimum. When you make something, you want it to be a maximum because you want the best cost to be able to make it. But we want a constraint on this, that we want the volume of the can to be 1,000 centimeters cubed. You know that 1,000 centimeters cubed is also 1 liter. And so depending on the kind of measurement you're using, if for the volume in centimeters cubes or liquid, you might be talking about a liter. But here we go. So I start out like this. I have an optimization equation. That's going to be surface area, right? So I think about what am I optimizing first? And there's a constraint that's given. The volume of the can has to be 1,000. So that's that second equation that I'm using here. So I take the consideration of the lateral area of the can with 2 pi r by h, and then you get an area of 2 pi r h. And remember, you have a top and bottom that has area, surface area, pi r squared. So my surface area equation would look like that. S is equal to 2 pi r squared plus 2 pi r h. Now, the volume equation that holds the constraint on the situation is 1,000 equals pi r squared h. So remember that we want our equation to be optimized. We want it in one variable. So it's very easy to take this expression for h and solve for h, actually. Sorry, to take the second equation and solve for h. So when we do that, then we're going to take that expression, 1,000 over pi r squared, and we're going to stuff it in to the equation where h is, and it goes right there. Okay. Now, what I'm telling you in this line is that you may want to check it out with your graphing calculator to see exactly what this looks like. It's very helpful. But after I put it in, notice that it simplifies because factors will cancel here and here. An r will cancel, and then there's only 1 r left there. So it simplifies to this nice equation. S is equal to 2 pi r squared plus 2,000 over r. So now I have that one variable model. Okay, so that's what we're going for there. Then in step 4, now we need to say, all right, we want to be able to express the surface area as one variable. We did it. Now what we need to do is our goal is to find r greater than 0 that minimizes the value of the surface area, S. So you can see from the graph that I have here, because I put in the graphing calculator, notice that I put it in as a function of x instead of a function of r. And you can see that I found the minimum of the graph on the interval. And so actually I just graphed it and saw where it recently passed the y-axis and what values would I need to go to, maybe 15, and see what it looked like, okay, before I even considered the domain of this function. But we'll get back to that. So there's our function, and what I want to do is I want to find ds dr. And again, I like using this because it gives me the idea of what am I comparing here. And we're comparing centimeters squared with centimeters, and very often I leave the units just like that in the final answer because it gives me that comparison of those two things. Sometimes people simplify centimeters squared over centimeters to just centimeters, but I think it has more value as a rate, centimeters squared over that. Okay, so let me get that out of the way. Okay. And let's go back to... So notice from the graph that for small r's, a tall, thin container, such as a piece of pipe, 2,000 over r dominates when you look at this equation, right? When S is large. For a large r, a short, wide container, think about the radius getting bigger. In fact, I'll throw in a GeoGebra in so you can see, like, playing with the r value. As r gets bigger, such as a pizza pan, then the term 2 pi r squared dominates, and A, the surface area, again, is large. So if r is really small, surface area is really large. And if r is really big on those circles on the top and bottom of the can, then the surface area is again really going to be large, okay? And that has to do with the fact that we have 2,000 over the radius r, okay? But then, so let's see what happens. That's just saying that we're looking for a minimum but there appears to not be a maximum or anything else that's going to go on. So let's consider, we're at the endpoints of the graph. So since A is differentiable, since the surface area, is differentiable on R greater than 0, an interval with no endpoints, it can have a minimum value only where its first derivative is equal to 0. So what we're going to do is we're going to take ds dr in this case. And so ds dr is just going to be 4 pi r. And it's going to be minus 2,000. And it's going to be r to the negative power of 2. But I'm going to rewrite that real quick. I'm going to write that over r squared. Okay, so now I have my derivative. So I want to find the critical numbers, right? So I'm going to set that equal to 0. So I have 4 pi r minus 2,000 over r squared, and that's equal to 0. So now, there are different things that you can do in this case. I can multiply both sides of the equation by r. This is really a preferred method of working when you have such a simple equation. So if I multiply both sides by r squared, on the left-hand side, I still get 0. So I have 0 is equal to, multiplying by r, I get 4 pi r cubed, and then I get minus 2,000. So it really is just kind of advantageous because what we're going to do is we're going to toss the 2,000 to the other side by adding 2,000, and then I'm going to switch sides of the equation using the symmetric property. So I'm going to do this. I'm going to say 4 pi r cubed is equal to 2,000. And then I'm going to divide both sides by 4 pi. Okay, so I end up with r cubed is equal to 2,000 over 4 pi. And then we're going to take the cube root of both sides to get r. Cube root of both sides. So what we're going to get is approximately, and we could simplify that if we wanted to. 4 goes into 2,000, right? So yes, you could, because that would be 500 over pi. It might be easier if you do that. So just a little stipulation with that. So you would have then r cubed is equal to 500 over pi. A little easier to digest. And then you would say the cube root and cube root both sides, right? So what we're going to get is approximately 5.419. 5.419. Now remember what we've just solved for. We've just solved for the radius. I guess I should have said r over here somewhere. So our critical number, r is our critical number, 5.419. Now what we have to do is that we have to decide something happens, but what happens at r is equal to 5.419. If the domain of S were a closed interval, we could find out by evaluating the surface area at the critical points and the endpoints and comparing the results. But the domain is an open interval, so we have to learn about what's happening at r is equal to 5.419. Now you can see from the graph, definitely a minimum value, right? By referring to the shape of A's graph, the second derivative. So remember I told you about the second derivative test. That's what we're going to use here. So I'm going to minimize all this stuff. Fun. Okay. And then what we're going to do is we're going to take the second derivative. So I'm going to use the Leibniz notation. So here's step 5. In other words, let's clinch the deal. So here we're finding the critical number, right, on this step. And we're not going to use the first derivative test with the number line. What we're going to do is we're going to say, is it a minimum? Let's clinch it. So what I'm going to do is I'm going to take ds to, remember, the second derivative of s with respect to r twice. Oh, put the 2 in the wrong place at the top. It goes after the d. The derivative, the second derivative of s with respect to r twice. So remember that you have to go back to what's convenient to do, right? So you have that right here. And if you recall when I first wrote it, I wrote it with an r to the negative 2. So what we're going to do is take the derivative with respect to r of the first derivative. So it's 4 pi r minus 2,000 r to the negative 2. So now I'm going to take that derivative and I get 4 pi minus, now it's going to become plus 2 times plus 2 times 2,000 is what it's going to be. So 4,000. And then it would be r to the negative third power, right? So now it's a continuous function. So I'm thinking, all right, well, let's see what we get for this. We need a sign. Now think about this. There's not a lot to do here because we have our second derivative. And it's greater than 0 throughout. And you can kind of see this. Let me write it up here. So it's 4 pi. That's a positive term, right? And then it's going to become plus 4,000 over r cubed. And that's a positive term. So when you add a positive to a positive, ds, the second derivative of s with respect to r, twice is greater than 0. And recall, now we didn't even have to put the r value in here. We could have done the second derivative test in full, but not necessary to put the value in because in this case, the second derivative is greater than 0 for all r elements of the domain of S. So we're good to go here. This is, in fact, the graph is concave up. So this graph, S, we can conclude, sorry, I'm running out of room here, is concave up. And we know that because the second derivative is always greater than 0. Therefore, r equal to the cube root of 500 over pi is an absolute minimum. Okay, and it's like I said, there's no endpoints. It's just going to keep going up left to right. So there's going to be there's no endpoints to test in this case, okay? So in this question, what are we being asked for? What are the dimensions to use the least amount of material? The video is getting a little bit long here. So I have r. So I have r is equal to the cube root of 500 over pi. But then remember, we got to get h. So then you're going to put h back in. And these are in centimeters, right? Centimeters. So then we have h is equal to, remember, you just go down to where I have h, 1,000 over pi times, and then you're going to have to put this quantity in. You might want to save this in your calculator to get the value. And there you have it. There's the height, there's the radius, so you've answered the question. Those are the dimensions that we use the least amount of material, okay? All right, that's it for the video tonight, and I hope you have a great day tomorrow, and I will see you when I see you. This is AllenVid out.